Okay, well, I want to say just like I'm so excited about, following up Muriel's talk because even if, we never met, we hadn't talked. I think, like a lot of the things that she said resonated with what I had to say. And yeah, so I'm really looking forward to this discussion. So the title of this is From ML for Astrophysics to ML for Climate, a journey across disciplines. So you would think that, I've taken this journey. Actually, that's not the case. I've barely started. Also, ML will have a very limited role in this talk. So the context for this, and I want to tell you a bit of the story because this is something that perhaps may be of interest for others, is that the Simons Foundation introduced last year. This fellowship is called the Pivot Fellowship. And the idea is that, it's for people who are actually, in a tenure track or tenure position, and they're interested in switching fields. And as we know, this is not an easy thing to do. So what they do is that they provide support by first supporting you for a year, which means that they pay your institution, so your institution is happy. And then, like you need beforehand to choose a host lab and mentors, and the mentor or mentors, they have to commit to mentoring you actually, and they are paid, of course, for their time. And then they give you a possibility to apply for funding in the new discipline. And so I feel like it's a really unique opportunity. I'll tell you a bit about, like how the idea came about for me, but I also want to point out that there is a new round of Pivot Fellowship application that is going to open March 1st, and the deadline is May 15th. And so, maybe something to think about. And you recognize actually there's like Xavier Prochaska and Albion Lawrence and other physicists. And interestingly, all the three of us are going into climate or ocean. So it's apparently a popular type of shift. So why did I think about it? I guess that one thing that I want to point out is that, yeah.
So sorry. So this program is really, I mean, it's like you're gonna be outside 5 years and then come back, or you really leave?
No, it's 1 year. Like the fellowship here is 1 year, and then you retain your academic position. So I'm gonna stay at CUNY, and I'm in a physics department. So actually, this is like not as outrageous as if I were going a completely different discipline. So I expect that I will keep maybe like teaching some astronomy classes and machine learning classes, or maybe also thinking about something new. And then you have an opportunity to apply for funding, which I think is important because clearly in 1 year I think a reasonable goal is to figure out what you want to work on, but you're not going to be like competent or competitive for external funding, really. So yeah. So for me, I felt like I don't know, something that I have accepted is the idea that serendipity can play a big role in our work life. I feel like this is something we accept for our private life, like we accept the fact that we don't know, when we will meet someone and fall in love and, end our lives for this. But somehow we work, I feel like, we have this idea that it's like very deterministic. And then, you do step after step after step. And then, hopefully you'll get to the result. And for me, I found that the most significant steps, even in my professional life, has often been shaped by completely serendipitous event. For example, my second postdoc, which I did with Erika Weiser, I just want to acknowledge the role that he has had in my career. Because he took a risk with me. I was coming from a very different field, and we had met completely by chance at a conference, and started bonding about these like terrible puns. As probably if the two of us, you're not surprised. Or the fact that I got my job at CUNY was mostly because like I sent the CV very late, and I had worked as a volunteer in correctional facilities, and I've been told this is like the one thing that made us like pick up your resume out of the pile. And or I don't know, like I sent I spent 3 years of my life writing this book that should finally be out. But again, like the reason why I sent the proposal was that I was sitting next to David Spergel at lunch, and he said, why don't you do that? And I was like, oh. So in a way, I found I gotten used to the fact that sometimes you don't need like this huge plan that has been going on for 4 years. So for me, I was a bit restless already. It happens to me every now and then. And then, for the book, I had been reading a bunch of papers and like geophysics, remote sensing. I was like, oh, this is really cool. Then, of course, Twitter. So I saw the ad for this lab that was opening. It's called LEAP. It's going to be my host institution. And this is an NSF Science and Technology Center. It stands for Learning the Earth with Artificial Intelligence and Physics. And then I guess a couple of weeks after seeing this, I saw the call for proposals. And so I felt like this was like my perfect storm, but it's not something that, I feel like it was perhaps brewing, but not something that had been in the making forever. So I want to say a couple of words about LEAP, especially because it's hosted at Columbia University. And so I think, especially for local people, maybe it's something that you want to know. As I mentioned, it is a center that really tries to combine expertise in physics and artificial intelligence, and sort of like tries to create a common community. They also have a commitment to broadening participation and education, which was something that, especially with my CUNY appointment, I was particularly interested in. So the way I went about this was a very humbling process, like in the it's called the press release about the opening of the center. They talked about the deputy director, Gail McKinley, and the director, Pierre Gentine. They're both, like Gail comes from an oceanography background, and Pierre is like more interested in like global circulation models and really every aspect of them. So, they are very well known, very respected researchers. And so I had to write, a cold email. And I was like, they're going to think I'm the retired engineer, I was like trying to send something where like, hey, would you like to be my mentor, without, sounding like a complete crazy. And even just setting the proposal, writing a proposal, it's a very generic proposal, right? They understand that you don't know anything yet. That's why you're doing this. But of course, you have to put together at least some ideas of things that are reasonable. And when you've been in the field for a long time, you're sort of used to be able to at least tell whether what you write makes sense. And I felt like in this case, I was just like, I had no idea. I was reading my paragraph, and I was like, am I saying that I'm going to solve astrophysics, the equivalent, or am I saying something that is like acceptable to a reader? So, at some point I had to set pride aside and, like email these very nice people that I had only met once saying, can you please check if this makes sense? So it was good. And just in general, embracing the uncertainty that comes with waiting to see if this big change is coming was interesting. But I'm very excited. So I still don't know much about climate. I'll tell you a little bit about what I learned. And I think perhaps like the most significant thing here, is this like a thing you think? Oh yeah. Oh, weird. Why does it go there? I am so impressed. Okay, I'm not gonna use it, sorry. But, so that's okay. I think, Oh yeah. Oh, okay. Yes, I like this. Thank you. As you can see, I'm very good with technologies. So in general, I think climate has a lot in common with some of the problems that we talk about in astrophysics, right? I think it is made of very, very many components. Right, you need to take into account the ocean and the atmosphere and the clouds and the land use and buildings and volcanoes and all of these things. And also something interesting, it happens on a sphere. There's also like, an interesting similarity. You have a multi-component problem, happens on a sphere. All these components interact with each other and feedback onto each other. A lot of their open problems come from a challenge about resolutions of models, right? You have things that happen on very small scales, you have things that happen on very large scales, and you have to put them together. And this is tricky, both because it's difficult from a physical perspective and because it poses like a computational challenge. So I'm sure you're recognizing things that we deal with constantly, and it relies heavily on simulations. In fact, I think that I have, in my like very brief journey, I'm now convinced that climate is an even more complex problem than the universe is, believe it or not. And one of the reasons is that, I mentioned the fact that, we talk a lot about, how to put together different scales, right? We can have like embodied simulations that encompass the whole universe. We have hydrodynamical simulations in large boxes. We have smaller simulations that can create things like realistic galaxies. And somehow, I think we have a little of an easier job studying these different regimes. The problems with climate, I feel, are two. One is that you still have all of these scales that you have to take into account, from like, tiny thing on a scale of centimeter, like aerosols, to clouds and tornadoes and hurricanes and, like cloud models, global weather models, and general circulation models on Earth scales. And on top of that, you have a time variable, which exists for us also as well. But a lot of times we can do things in snapshots, or in any case, the time scale of evolution is a slow time scale. And this is really not the case here. So each of the problem is not just on a different spatial scale, it's also in a different time grid. And then the other thing that I think is different is that we sometimes can actually study pieces in isolation. We know that it's not correct, but it is generally correct. To first approximation, it is correct. Something that I learned recently is that the biggest problem in circulation models, and when I'm saying the biggest problem, I'm saying the things that gives you the largest amount of scatter, even in basic predictions, such as when are we going to get to that 2 degrees warmer? Is it going to be 2035 or is it going to be 2060? And this comes from these scales. So it's really hard in that case, on the small scales, things like the clouds and aerosols. And so it's really hard in that case, or small eddies, to say, okay, I'm going to study the large scale independent of the small scales. Well, I feel like that in astro, the fact that, things come from linear perturbation theory, and, we have this idea of like, seeds growing, helps a little bit. Another things that I've thought about in my work is, like how to develop assessment metrics for a good models are. And I feel like this is also like, a big thing in climate. For example, here you have like one of these is like an actual Earth satellite observations, and the other ones are simulations. And you can see that they do pass a visual inspection, just like in this is like, a set of interspersed real and simulated galaxies. We're at the point where we can generate things that are realistic. But then, we still have the problem of like, okay, beyond the visual test, what's a more rigorous way of assessing whether or not our models are realistic, both at the sample level and at the population level? And this is something that, of course, we talk about a lot, and we heard during this week a lot of thoughts about this, and they're also starting to think about. So I feel like the nice part, like I guess the nice point here is that there are a lot of opportunities for crosstalk between the communities, right? It can be scientific applications. We can do modeling. We have similar problems: simulation-based inference, subgridding, emulation, development of metrics, outlier detections, equation discovery. And this is just a few, right? We can also, I think, we have a lot to share in terms of community-based practices. I don't know much about this community yet. I feel like it's also, in a way, a younger community, right? Because I mean, like scientists have been doing climate science for a long time, but I feel like that, it has really increased and, welcome people from different backgrounds in the last decade or so. But, I thought, for example, of climate bites, like we have astro bites. Wouldn't it be nice to have climate bites as a way of making, climate more accessible, even to younger students? And then in general, of course, I think climate is a booming job market, and I think a fulfilling one, right? Like I think we know that we have a lot of students trained in like astronomy and physics who may be considering leaving academic astronomy. And I feel like this could be like a really nice field to consider as an alternative. So how can we do that? Well, this is, going back to what we're talking about, cross-disciplinary research. I feel like that there is mostly from funding agencies, this chimera of cross-disciplinary research and how it happens. That, you have a person who's an expert in one domain. Let's say there is like astrophysics, and then a person who is an expert in another domain. And, like in the 2000s, when I sort of like started out my PhD in 2006, it was like statistics. We had to go and talk to the statisticians. Now, now they call them data scientists, right? But it's the same idea. The idea is like you take these two people who know about two different fields, you put them in the same room, and they will talk and produce science. And I feel like that this is very unrealistic and just, I don't think it can work this way. So my, I don't know, somewhat controversial opinion is that there is no low-hanging fruit in cross-disciplinary research. I feel like that it has something that has a ton of potential, but it has something that I think really needs and deserve resources. So I think, first of all, I believe that you need an overlap of knowledge domains. I think it's okay if there is one person who's more expert in one field and another person who is more expert in another field. But I think there needs to be an overlap. And in my opinion, this is not just a language barrier. I mean, this is a part of it, the part, okay, we call them variables, you call them features. I think, it is one part, but I don't think it's the main part. I don't think it's just a matter of adjusting language. I think that, as we know, a lot of times when we do science, we cannot do it blindly, right? You look at something, you're like, this looks weird. And you cannot say it looks weird if you don't know what you're talking about, what the expectation is. Now, I think this is the good part about collaborations, like you only need like one person to be able to pick up every single details. But I do think that, like you need to be able to spend time with the other community and build that domain knowledge before you can do something meaningful. The other thing is that this interaction needs to be sustained and nurtured. Right? Sustained means that it takes time. And I feel like this is probably the thing that is hardest to do, as we were mentioning, right? And nurture means that you need to have some meaningful mentorship. It's not something that happens just because of the act of being in the same room. Right? I think you need to have some commitment in the other community to welcome you and to value your contributions and to spend time teaching and helping you understand. And so both of these things require money, right? Being able to spend time doing this and having someone who is willing to help you takes money. The other problem that again we mentioned is incentives, right? Like it's not just that you need to have resources for this, it's that people from both sides need to have a motivation. And this I feel like is even the trickier part. So I have an example from a previous pivot that I did. It was in Astro, right? So like a minor one. But as I mentioned, for my first postdoc, I was working mostly on like CMB, both from a theoretical perspective. I was doing modified gravity theory, like the sort of Jordan-Brown sticky type, not Mond type. And then I was also part of the Atacama Cosmology Telescope. And so we were doing analysis of CMB data. And so I learned how to do these things there. Then for my second postdoc, I started to do spectral energy distribution fitting. And I think it was interesting because in this field, there were barely error bars on any plot. You would only, mostly people were doing sort of like, like best fit through chi-square. So it was interesting because I could import some of the things that I had learned here. And, I wrote this MCMC ICD fitting code called GalMC, which of course was inspired by CosmoMC. And it was the first public code. Not that this was like, life-changing work, but I think it was like honest work and, like a meaningful contribution that came from a different community. So what's wrong with this? Nothing, but it took me 2 years, right? And I think I was lucky that Eric, that I was working with at the time, understood that it would take 2 years. It is something that is not common for a postdoc to be able to do. Right? And of course, even to write this code, I had to learn all the different bits, or at least some of the different bits that go into galaxy modeling. It's not something where I could have just said, haha, here, let me build these architectures and everything works out. And this is, I think, the tricky problem. I feel like that there's a lot of potential in cross-disciplinary research, but you need adequate investment and even more there should be an understanding that advances take time and are higher risk. And I think our system is not set up to reward those. This is something that we said already, and I don't know. I think this is like the hardest piece to change, right? And this is also related to Mark's question. How do I say to like a student or a postdoc to venture in something that is higher risk, when you know that the expectation is that you have like 1 million papers on the same topic, and so you've become the world leading expert on that one, and this is usually what you're told that you need to find a permanent position. And even later on, right? Okay, in many places, to get tenures, to get promotions, you need to show that you have a lot of funding and a lot of papers, and this usually it's much easier to do on something that you're already an expert of. So again, I don't have a solution, but I think this is the main problem, and it's something that if we want to do interdisciplinary research, this is something that we have to have a big conversation about. All right, so for me, for the next pivot, again, I'm sharing this mostly because I feel like it's been helpful for me to use it as a framework to think about what I want to do. I'm hoping to learn fundamentals of climate science, so creating this sort of domain knowledge. And I have sort of like a guaranteed sustain and nurture interaction for 1 year. Clearly, this is not enough. So I think in the end, this will depend on whether I find a new community. But I think the last piece, the third piece is finding out what I want to do and what I can contribute to. And I don't want to be the person who does ML. I don't think anybody here wants that either. So I think the third piece is really what can I bring to this field that is me. And I'm a bit obsessed with this diagram. I'm sure it has a different origin, I don't know. But the first time I heard about it was from Dr. Ayanna Elizabeth Johnson, who was one of the co-hosts of the How to Save Planet podcast. I really like it. Sadly, it's been canceled a couple of months ago. And I think, the idea here is to consider these three bubbles. One is what needs to be done. You can think about it, what can be done, what's interesting, right? Maybe in research. One is what you're good at. And the third one is what brings you joy. And try to work at the intersection of these three. So I've been thinking about this over and over and over. I have identified some things, so this is my bring joy. This is what I can do or I'm good at. And I found these things. I love connecting people. I know a lot of people, so I think this is something useful that I could do. If I also met people in the other community, I love when people say, email me and say, hey, I'm trying to do this, and can you help? And I can say, yes, this is another person you can talk to. I love solving simple problems with code. I have to say simple. Here I'm saying things where it's easy or possible to get insights. Like not too involved. And I love to work in small teams and co-advise and do these things. I've abandoned like very large collaboration a long time ago. I just realized that this is something that I can't. It doesn't bring joy, and I don't want to do it. There are other things that I could possibly do, like solve hard problems with code. But I feel like I've realized I don't really spark joy, so I'm hoping to stay away from this. Writing grants, another thing I think I'm reasonably good. And I didn't mind writing these proposals, but again, a long time ago, I stopped writing big grants because I just felt like the odds weren't worth it, and I was lucky to be in an institution where I could get away with it. And I also think I'm reasonably good at communicating difficult concepts, and this I feel like is right here at the at the margin. I think in some contexts it does bring me joy. I like teaching and I like talking, but I don't like psychom usually. I don't know. So but there are also things that bring me joy, but I cannot do such as these. I keep them to myself. But I think the big challenge is to understand. I really have no idea of where this is useful or can be done. Box will end up. Hopefully not there because there is no intersection. But I think this will be the challenge. All right. Sorry. I guess I started also a little bit late, right? So let me finish with possibly the most useful part of the talk, which is what we've been thinking about. If people are possibly thinking into a transition to climate science, what will be useful skills? What are the most transferable skills? And maybe what are the barriers? And of course, in this case, as I told you, I cannot really speak about that, but I have asked people. And so I've asked 4 brilliant people that I will introduce here. The first one is Kirsten Hall. Kirsten is currently a submillimeter array fellow at Harvard CFA, and she was one of the 2020 Schmidt Fellow. The Schmidt Fellowship is a fellowship for a pivot that is like for people right after their PhD. It's a 2-year fellowship. So she was in the 3rd cohort. And for her, the focus of her project was on atmospheric physics and remote sensing, with the final goal to identify focus spots for emission and pollutants, and perhaps, an eye finally to policy. And now she had deferred her postdoc for this, and so now she's sort of like, back at CFA to finish up, but I think, she's still very much hoping to work somehow at the intersection of this. And, she comes from a PhD in astrophysics at Johns Hopkins. She was actually a Toby Merridge student. Second person, some of you may know Chris. He's currently a postdoc in climate modeling at NYU. He's working with Laura Zanna and John Bruna, building pieces of climate models to account for different scales, as we were mentioning, using machine learning, and also a member of this M2Lines collaboration. He's a recent climate expert, and before that, he did a PhD in astrophysics at UCL, and then he was a postdoc at NYU and also spending time here working with Shirley on machine learning application in cosmology. The third person is Carol Lamb. She's an associate research scientist at Columbia University and also part of LEAP, my new institute. And she works at the intersection of observation and high resolution modeling. And in particular, she's trying to understand the role of aerosols and clouds in climate. And she's already a climate expert. She was at NOAA from 2016 when she got her PhD to 2021. But her background is in physics. She has a PhD in physics from University of Chicago. And finally, Sarah Shemek. She's a postdoc, again, at Columbia University, and she's looking at machine learning for parameterization of turbulent fluxes and equation discovery. Already a climate expert, she did a master's in Earth System in Trieste, actually at ICDP, and then she did her PhD in climate science at École Normale. But her bachelor and her first master's are actually in condensed matter physics. And so I asked them, okay, what's the essential domain knowledge that you need to have? So I don't know, what's your first guess? Actually, the first one is kind of a skill, but this is what everybody was telling me. Say again? Oh, programming. Okay. Other curiosity. This is like a bit more domain knowledge. I talk about skill, but it was partial differential equations. I was like, oh, I see. Everybody was like, this is the name of the game. Fair enough. And then, they mentioned things like geofluid dynamics to understand things like atmosphere and ocean, a general understanding of how the different pieces of global circulation models work. And I have here, I don't know what happens. I realize I cannot actually click on a link, but maybe I'll, I don't know if the slides are so. Oh, thank you. Thank you, Des. I forgot that you have this sort of like godlike powers. Right. So this is, a course that they had a LEAP last year with the idea of putting together climate scientists and data scientists. And so it comes with a lot of like intro material. And so I figured this was like also a good resource to point out to. Thank you. Thank you. Okay, the second bit is, what are valuable skills that physicists have in climate? Now, this is a bit more of what we said, what we were talking about. What do you think will be the first one? We had programming, curiosity, what else?
Modeling.
Modeling, that's a good one. So I think, the biggest advantage here was the idea of thinking like a physicist, right? And I feel like sometimes we forget, like they tell you, study physics and then, you can do everything. And, it sounds like trite, but I think it's true. Because I think that it's true. There's like a very rigorous training in thinking about problems, right? And so I think the two aspects that came out were, one being question driven, not like technique driven. It's not like, okay, I want to use ML for this, but it's like, okay, what question am I asking? How am I going to go about it? And also the fact that perhaps, even when you see a difficult problem, you have seen some of them before. And so you're, curious perhaps rather than intimidated. And other things were in general problem solving, and an important one that I think we also think about a lot, like being able to think about what solution goes with what problem, reading papers, and sort of like at the end of this, the numerical skills. I just want to mention PDE again, but there was data visualization, exploration, and machine learning. And even if it was prominent, in terms of like everyday research for many of these researchers, I feel like it was never mentioned as, like the difficult bit or a barrier. And so this is just something that I want to emphasize. What were the barriers? I think, this, I don't know if there was really like a ranking, but I think in general, the idea of being able to have, like the commitment of the climate community to the success was a big one. And time was the other big one, right? So in general, the availability of continued funding and the freedom to fail. The sheer complexity of the problem was something was mentioned, and by several of them, and the recommendation was to be like, okay, don't try to do everything at once. You can learn piecewise, and maybe like the idea of a mentality shift. I feel like we have all developed an idea of how it is that we go about problems, and this is something that may change when we switch fields. So the idea of like being open to like sort of leaving behind some of our schemes was another one. All right, I think that this is it, more or less. So, from what I learned in, these very beginning steps of this journey that I will properly start in the fall, is that I think that I hope, and I also expect that there will be strengthening connections between the climate community and the astronomy and physics community. And, I'm scared, of course, about this, but also excited, hope to find my spot in the Venn diagram. I really hope that in a few years, I can be a person where, if you're interested in doing this career transition, you can come to and I can help facilitate them. And I am very excited to showcase all the physicist talents that make them qualified for careers in climate. And I should say that, probably machine learning will not be one of these because, I think it's useful. And you should also buy my book. I think it's here to stay, but unlike everything else that you do, it's not rocket science. Thanks.
Time for questions. Anyone? Next week.
So, giving advice to students, like particularly PhD students who are interested in machine learning, there's a tendency to be kind of broad because, it's a hammer and there's like a lot of nails. But like, is that a good idea? Like for their career and getting a postdoc? I mean, as you know, it's very difficult to be broader and to go from one topic to the other. And, you've had such a successful career with this, but not everyone has that same story. So like, would you advise someone to do that? Or would you advise like a PhD student to be like, try to be a little more narrow until they become more stable in their career?
Well, I guess this is very personal. And as you mentioned, we are all shaped by our own experiences. So I am, I'm a little hesitant. But I think for me, I would advise a PhD student to always be driven by a science, to be like, to have a story to tell, which is a science-driven story. And I think, I don't think, like, I feel like the technical part, the machine learning part is something that it's easy to learn. Now it has become a bit of a buzzword. And so I feel like, if there is a chance to incorporate some of these in a project, I think it's a good thing to have. But to me, the idea of like having a student and be like, okay, I'm interested in machine learning, I would probably think, even for me personally, I don't know if this is a good match. Because I think really, I don't know, I think it's a strength that we have, like that we can think about science. So as much as I love techniques, and I've always been interested in techniques, and maybe not driven by, like a big overarching goal, I feel like that, this is what we do, right? It is science. We do not build systems. We answer questions.
Mark? Thank you very much, Viviana, for the talk. Just a comment on this before I ask my question. Machine learning can be science, and it's science. So
Yeah.
when you tell machine learning researchers, we
No,
do science,
it's
you
true,
do
yeah.
technique.
No, yes, I don't want to be, I'm just
They are
saying maybe it's
scientists.
not like my science. That's what I mean. Yes, fair enough.
Anyway.
Yeah.
In many of the examples these people you showcase, lots of them are young. I mean, they did their PhD in physics and then they transitions for a postdoc, and which a postdoc could be seen as still, you are learning, let's say. So it's an early stage in your career, and it's, I understand this switching at this stage. Now, later in your career, it's a different thing, and so I was wondering if you know more people that did that, at a later stage, and how I was wondering how they can contribute to the field, and probably you're asking yourself these questions, but I know if you know some other examples of this successfully transition later on.
I don't know many. I think, as we know, I think that it is uncommon because I think it's difficult and our reward system doesn't work that way. I know Sarah Bridle, right? You may remember her. She was like, in cosmology for a long time. And I think now she has like a successful company that does food science. And I think this was already like a faculty level. I'm trying to think. I mean, I'm sure there are names, but for sure there are few and far in between.
So maybe, Viviana, along this line, so I mean, this might be a weird question, but once you are tenure, you cannot do whatever you want. I mean, it's not maybe.
Yes.
It's not maybe easy. No, I mean, it's.
No, I think it's a fair question. You mean like, why do you need the structure to do what you want is the question? Like, could I have done this without this pivot? I mean, or anybody.
Why is not maybe easier at the faculty level to do this transition more than maybe at the postdoc?
I think because of what I was mentioning, even assuming that you're not interested, like you are exhausted, the promotions that you want to go for, and like you're okay not having students. I feel like that getting yourself to a place where you can do something meaningful, I think it's really hard without mentorship in particular. And so I feel like this is, I think clearly at the faculty level, you have like job stability. And I think it's easier to say, okay, I'm not going to apply for grants, right? But then, like around you, then you become like the only person that you're working with, because, switching to a new field and, like writing a grant is something that, is going to take a few years to build. This is not, but I think to me, it's really that, learning something new, as we mentioned, is something that is difficult to do from a book. Right. And so in a way, like showing up in a new community and saying, hey, I want to be part of this. I think it's possible, but it's hard, right? Compared to having someone who wants to make meaningful introductions. So I think I think technically it's true. And, maybe you can start from like collaborations. But I think collaborations are more likely to be like, okay, there is something that is maybe a technique, and then the other person, the subject matter expert, and maybe you do it. It's possible. I mean, there is like the astrostatistics groups, I think, that we have. I can't remember the name of the association now. I think they've been like, one successful group that has done this for years, like has been building community for many years. But I think it's not, technically possible. It's not easy.
Marielle has a question.
Yeah, I wondered, it's one thing it's interesting to talk about where we can go from the astro or astrophysics communities into other disciplines. I wonder if you see it as particularly difficult for people from other disciplines to come into our community, and if there's other changes you think we should make to be more accessible in that way.
Yes, I found that it's very difficult. I work, because I work with a lot of these numerical techniques, I work with several students like in statistics or computer science. And I think, there's been especially like a couple of them that would have loved to join astrophysics, that maybe they've written papers, but they really struggled to find jobs. And I found that the biggest barrier wasn't necessarily like the subject matter knowledge, but this sort of like mentality shift. This is at least my impression. This is what I was referring to when I was talking about the difference. I didn't mean to imply machine learning is not science. I'm just saying that for for astrophysics, I think that if you want to do machine learning and that's your main goal, maybe that's not the best match. So I found that the sort of mentality shift to be question driven rather than method driven was hard. I don't know if maybe we could be more understanding and more welcoming as a community, but I found that this is maybe something that it's harder to shift later in your career. I don't know. I don't have many examples.
Sultan and then Festa.
So I think something I have been thinking about a lot, when I apply for like faculty jobs and how would I run my group, and I think like for the students, one can actually take advantages of like most of the universities now have like these data science initiatives, where their mission is to help other like all the departments like university-wide things, and they have seminars and they have talks. That's probably also true in like the statistics and the applied math departments. So I think encouraging the students to attend these talks, and like, because I think like if you talk about interdisciplinary science, right, you need to connect to people and interact with people and talk to them, right? And I think pushing them to seek affiliation or to seek attending like these talks and interact with the other, like through the data science center in particular, I think might be useful to start at least collaborating or joining, and or even being aware, right? Because we are not really even aware what's going on in different projects and how we can connect them to what we do in astronomy. So
no, I think this is a great point. I think we definitely need to take advantage of this. I think my take is that maybe the burden of this is harder to put it on the student. But I think the way to do it is like, can two people co-advise a student? And I think this is, like maybe something that has a higher chance of success. Because I feel like it's on the students to make the connections. And then, like there is in a way no incentive for, members of the other community to mentor them and to welcome them. I think it's a bit harder. But I feel like if as a faculty member, we are the ones who reach out and say, hey, can we think of a project that, we can do together? Then I think this is, something very promising.
My question is more related to the previous question about like mentality shift. So is it just mentality shift, or is it also a difficulty because of all the background knowledge that one needs in physics in order to be able to apply it?
I mean, of course, it's everything. I just felt that, my experience, I think, with the students that I've had was that was harder somehow. I feel like, like we are talking about, obviously all smart people. And so, yes, catching up on the background, of course, is like a big effort. But I felt that, even in interviews, for example, I felt that the reason maybe they were having a hard time being chosen, even being, very close, was this, like just like the habit of thinking about, okay, this is a problem. What is it I'm asking? What is it I want to know? How am I going to get there? And this seems to be, it may be just anecdotal and like, I don't know, but this seems to be like a bigger obstacle in the experience that I've had.
Any other question or comment? Yeah, please.
This was an amazing talk. Thank you.
Thank you, Kartik.
A really quick question. Is there an archive in climate science?
That's a good question. I feel every time I, like look for a paper, I've never found like an archive version. So I want to say no, but I may actually be ignorant about this.
Okay.
I don't know if there's like the same, like the equivalent.
Because I think
thing.
that's one of the things that helps us a lot in just a preprint server and an API has been key for like my research wouldn't be the same without it.
Yeah, no, I don't know. Yeah, I agree. I feel like I'm also in an institution that basically has zero access to any published journals. So, okay, it's a very good point. Yes, and I want to say no, but I'll inquire more.
And by formation, Viviana, I mean, usually these people are physicists, are chemists. I mean, what is their?
It's a very good question. So, for example, Pierre comes also from a physics and engineering background, although started to work in climate quite early. I think some of them are like earth science departments and like earth science. But I think there are a lot of physicists. I feel like in this group, I think about half of the people have somewhat of a physics background. Although I think the diversity of the community is also an interesting thing. I feel like that now probably you see people from like different paths. I think is what makes it vibrant. But definitely physics is a prominent component.
Okay, so if there are no more questions, let's thank Viviana again.
Thank you.